second link or the third link. And this velocity has to be determined. That's how we move from one link to the other link and so on. So this is one point. And we will see later on how it is to be done. Then in case of velocities, there are two types of velocities we will come across. One is the absolute velocity. That is a velocity that is normal, no velocity at point A, B, C, with its direction and magnitude. And the other one is the angular velocities, omega, okay, or the rotational speed in RPM. And you will find in most of the cases, the angular velocities and the number of these things are much more than it. And most of the links are some sort of having a rotational motion. So for velocities, whether it is angular or absolute, we have to determine or must be given the direction and magnitude of all these velocities. Direction and magnitude. So if we only determine the magnitude, it is not enough. We must also know the direction in which it is working. In case of angular velocities, it's a rotational value as well as is the direction of rotation, clockwise or anti-clockwise. And then, in order to start our analysis, we have to draw the mechanism to scale, because you will see that the velocities, particularly the angular velocities, are proportional to the length of the links. So drawing the mechanism to scale is very important. And for that, we need to choose a space scale at the very beginning. For example, we can represent a link. If it is say 500 or 50 centimeter, then you can represent 5 centimeter as 1 millimeter on drawing, and thereby the length of the link to be represented in the drawing scale as 10 millimeter and so on. So this is called space scale. There are some methods where the velocities have to be drawn or determined separately through a velocity triangle. But there are methods where the velocities have to be determined directly on the mechanism itself. So that's why the drawing of the mechanisms to scale is very important. And the direction of the velocities are also depends upon the orientation of the linkages. So if we do not draw to scale, we won't be able to know what is the exact direction of the velocities. So this is about space scale and drawing the mechanism. And for that, we need to know the length of the mechanisms, and all these things will be given, length and orientation of the mechanism for a particular instant. Then to determine the velocity again, we must choose a velocity scale. For example, say 5 centimeter per minute of velocity is to be represented in 1 millimeter on drawing like that. And the scale has to be convenient. Where very large velocity is there, we can, where large velocity is there, we have to take a large scale. Where a very small velocity is there, we have to assume a very small scale, such that appropriate length of velocity comes on the drawing. It should not be too small, it should not be too large. Now, what are the methods? There are a number of methods, at least 3 methods are there, which we will learn to do about. One is relative velocity method, and this is the most general one, and probably in your mechanics class also you have learned about this. Do you have any idea about this relative velocity method? Any idea about this? How it is done through relative velocity method? Yes? I asked a question. I want an answer to that.
Sir, we have done the basics of relative velocity.
Hmm? Relative velocity method you didn't study in your mechanics class?
Yes, sir.
Okay, the method is same. There are two types of velocities. One is called absolute velocity and the other one is relative velocity. Okay, and in very brief, what is this thing? That if you have 2 points on the same body, A and B, and if we know the velocity at A, if it is known, then the velocity at B should be velocity at A plus velocity of B with respect to A. And that's the equation. And of course, it's a vector equation. Okay. Now, and this thing has to be determined through a velocity triangle. And the shape of the velocity triangle is like this. We start from a point which is called pole. This is O is the pole. And the velocity at A is represented by OA in magnitude as well as direction. And the magnitude has to be represented through a scale. So if it is 10 centimeter per second, and if you choose 1 centimeter per second as 1 millimeter, so this should be 10 millimeter in length. Okay. Then this is the velocity of B, OB, in magnitude and direction, and this is the relative velocity. So relative velocity of B with respect to A. So the direction has to be accordingly. So if it is the velocity of B with respect to A, then it is from A to B. Okay, but if it is the reverse, that is velocity of A can also be represented at velocity of B as velocity of B plus velocity of A with respect to B. Then in the case, the triangle will be drawn in the other way. That will be VB, OB, it will be BA, and it will be OA. Okay. So this is called velocity triangle, where absolute velocities are represented by the vector which starts from the pole. So OA represents velocity at A, OB represents velocity at B, and AB represents velocity of B with respect to A. So this is a relative velocity, and the relative velocity always connects the absolute velocities. So it is never drawn from the pole. So that's how we identify them. Okay. So in very brief, relative velocity method is that where velocity at a particular point on the same body, same link can be determined by summing up the velocity of a point on the same body, some other point plus the relative velocity between these 2 points. So that's all. So this is the relative velocity method in summary. Okay. So that is universal and that can be applied for any other places. The next is another method which is exclusively for velocity analysis. Is called the centro method and the instantaneous axis method. Instantaneous axis method. So here the concept is that if we look at the links and the joints, there are members links working like that. They are fixed at some point and moving. So there is rotational motion. So it has, if this is the link and if it is fixed here, so it is rotating about this link. So it is center of rotation. Similarly, there are other links which are also rotating about the center. But there may be a link which do not have any fixed center of rotation. So what is the difference in the motion of those links which are having a fixed center of rotation and the links that do not have a fixed center of rotation? The difference is that the center is always fixed. So we always know, say here, what is the velocity at A? It is omega, rotational speed, multiplied by distance OA. Okay. Similarly, at point B, it is omega multiplied by O to B. That's all. But imagine that this center is not fixed and the link is floating and its center of rotation goes on changing with respect to time. Then, in that case, its center of rotation is called a instantaneous axis. Okay, the axis of rotation is instantaneous because it keeps on changing. So So using that concept, we can determine the velocities on different links of a mechanism. And this is called instantaneous axis. It is also generalized to call it a centro method. And there is also a theorem which tells us about how many centros or how many instantaneous axes there can be in a mechanism having n link. Okay. And it's very simple. The method is that the velocity is equal to the angular rotation multiplied by the length of the link, or omega into distance from the center of rotation. So in this case, this is the link. OA is a link, say L. That multiplied by omega is the velocity at A. But at some other points, what is the velocity? It is same thing. That is omega into distance of this point B from O. So this is how omega into this. So by using this simple concept, we can determine the velocities on different links. Okay. So the concept is that if you have a center of rotation, so velocities will always be perpendicular to the line joining the point and the center of rotation. That is this. It has to be perpendicular because it is rotating about this, and its value will be this omega into this length multiplied by this length and this omega. Okay, is it understood?
Yes, sir.
Okay, so this is a very handy method. This gives us a very quick solution, quick determination of the velocities. And in order to apply this method, we do not need to draw separate velocity polygons like we have to do in case of relative velocity method. Here we do it directly on the mechanism itself. And when doing it, you should try to use different colors just to differentiate between the actual mechanism and the velocity lines and velocity representations. Okay, so this is instantaneous axis, or the central method. And the third method, actually this method is not there in the Gauss-Molnick book, is resolution composition method. What is this method again? It states that, say, this is the link AB. And if we know the velocity at here, we want to determine the velocity at this point. Okay. Now, here, the approach is like this, that any velocity on any point on a link can be resolved into two components. One along the link, and the other one perpendicular to the link. Okay. So we resolve it. So this is the velocity. We resolve it. So this is the axial component of velocity. This is the perpendicular component of the velocity. So at point B, where we want to determine the velocity, we must also have a axial component as well as a perpendicular component. Now, this method tells us that the axial component, so the component of velocities which is along the link, will be same at all the points on the link because they are considered as a rigid body. So whatever velocity at A along the member, so velocity at B along the member will be same. So this part and this part will be the same. This component and this component will be same. Okay. So one part of the component can easily be determined by resolving into two components, the known one. So this part and this part is common, and to know the other one, we must the other component will be perpendicular to this, and this component we have to determine in magnitude, or alternatively we must know the direction of the final velocity, without which you cannot determine that. But only this assumption is enough to determine the velocities at some other point on the same link by this method, which is called resolution and composition methods. Okay. So, any question on this? Any question?
No, sir.
Okay.
Sir, velocity along the along the link will remain same.
Yes, along the link has to be same. But perpendicular components will be different. And you can also see over here, and perpendicular components will be different because of the rotational speed. Like this, say, if it is a fixed member, it is a center of rotation. So what is the velocity here? It will be perpendicular to this line, joining these 2 points, and uh, distance into omega. So as distance increases, the velocity will increase, and so on. So it depends where the center of rotation is. Okay, similarly, that's why the perpendicular components will be different, but the axial components will be same. Otherwise, they don't remain a rigid body. So if the speed here and the speed here, they are different, that means the points are moving with respect to each other, and there is some compression or extension is there. So this is about velocity analysis, the three methods. So most general one obviously is the relative velocity method, and in most cases we use that, but most convenient one, depending upon the configuration of the mechanism, is this centro method or the instantaneous axis method, because it generates solutions very quickly, and you can determine the velocities very fast. And regarding acceleration, so rate of change of velocity is acceleration. So what are the steps to be followed? So first you have to draw the mechanism to scale as usual, space scale. And of course, one thing I didn't mention over here, you have to complete velocity analysis first. Without making or completing velocity analysis, we cannot do acceleration analysis, because some of the acceleration components depends upon the velocities. Okay, so in between these two, you also write one line that first you have to draw the mechanism to scale, then you have to complete the velocity analysis and determine all the unknown velocities of the links, particularly the output link where we want to determine the accelerations. And then we go for acceleration analysis. Acceleration, like velocity analysis, you have to select the acceleration scale, and then we can draw the accelerations. There are certain other methods are there, but the most general and most convenient one is the relative acceleration method. But in case of acceleration, things are a little bit complicated compared to velocity analysis, because in velocity analysis, we knew that there are only two components. If it is a relative velocity method, then one is absolute velocity and the other one is a relative velocity. And the relative velocity is perpendicular to the link joining these two. That I will discuss later on. But in case of acceleration analysis, there are double that number of components. But the expression remains the same, that the acceleration at point B is acceleration at point A plus acceleration of B with respect to A. So nothing wrong in that. It's simple, plain relative acceleration velocity vector expression. Okay. But in case of acceleration, there are two components per accelerations. Okay, one is called normal component or normal acceleration, and the other one is tangential component or tangential accelerations. And normal and tangential, as usual, they are perpendicular with respect to one another. Okay, so we have to break it down into this. So the vector expression has to be broken down into two. Acceleration at point B is a vector sum of acceleration normal at point B and acceleration tangential at point B. Acceleration at A is a vector sum of normal acceleration at A and normal tangential acceleration at A, plus relative acceleration of B with respect to A. Will have two components. One is the normal acceleration, normal relative acceleration, normal tangential accelerations. And each of these combination of normal and tangential accelerations are perpendicular to each other. This is perpendicular to each other. This is perpendicular to each other. But one thing that is helpful for making this analysis is all normal accelerations. All normal accelerations are directed towards the center of rotation. So if we know the point link where the point B is there, its center of rotation of that particular link, we know that the direction of this component of acceleration will be towards the center of rotation of the link. Similarly for A, but in case of relative acceleration, what happens? So if it is this relative acceleration of A of B with respect to A, then obviously the direction of this relative acceleration will be towards A. Why? Because from the name itself, we know the acceleration of B with respect to A. So it's meaning that as B is rotating with respect to A, that means at center towards A, towards that direction. Okay. So the direction is from B to A. So that will be there. So that's how the relative acceleration directions are given. So the direction of all normal accelerations, whether it is absolute or relative, will be directed to its center of rotation or apparent center of rotation. So that's how we get it. Okay. So if it is acceleration BA, then from A to B, okay, with respect to A, so it will be towards the center of A and so on. And direction wise, I can show you that if it is say for linkage, then if this member is rotating in this direction, so its normal acceleration will be directed towards this center. This normal direction will be towards this center and so on. Okay. And so far as instantaneous center of rotation is concerned, so this member, this is a 4-bar linkage, this is a fixed member, this is a member which is fixed here, so it is only rotating about this. This is fixed here, so it is only rotating about this. Okay, but this member, it is connected to this and this, so it doesn't have any fixed center of rotation, but it's also rotating. And the thing is that its center of rotation is getting changed with respect to time. So for a particular value instant, say for this instant, it will have one center of rotation. As this one moves a little bit towards right, and say the theta increases, say at this moment it may be 50 degrees, something like that. Then if you reduce it to 30 degrees, so it will move from here to here. It will move from here to here. So this will also change its configuration. So it will have its center of rotation change. So for this link, it will have an instantaneous axis of rotation. Okay. So the instantaneous axis method tells us about how to determine its center of rotation and so on. Okay. So what is done is this. Okay, let us start from the 4-bar linkage itself, then I will come back to the other ones. Okay, so here this is the 4-bar linkage. It is having a fixed center of rotation. So if it is moving in this direction, its velocity will be in this direction. So as it is moving in this direction, this link will also move in this direction. So its direction, but velocity direction is in this direction. So velocities are always perpendicular to the link if it has a fixed center. Okay, always. Now, what about this link? If we consider only this link, its velocity is in this direction at point A. So its center axis must be somewhere perpendicular to it. For this point B, it is fixed at this point. This velocity is at this point, so its axis must be perpendicular to that. So these two lines intersect here. So this is the center of rotation for the link 3. So for link 2, this is the center of rotation. Link 4, this is the center of rotation. For link 3, this is the center of rotation. But for link 2, the center of rotation always remains at this here. For link 4, the center of rotation always remains here. But for link 3, its center of rotation changes. And that's why it is called the instantaneous center of rotation. Okay, and it is to be determined in this way: velocity perpendicular to the velocity, velocity at B perpendicular to the velocity, and wherever these two lines meet, that is the center of rotation of 3. So that's how instantaneous axes are determined. Okay, is it clear?
Yes, sir.
Yes, sir.
Okay, let us see then how to determine the velocities. Start with a 4-bar linkage. So this is the forward linkage. So what are the things that we require to start the analysis? So first of all, this length and everything has to be given, and this angle theta has to be given. That means the linear dimensions for the linkages, for the links have to be given. Say L2, L3, L1, L4 has to be given. And the orientation also needs to be given. Otherwise, we don't know, we won't be able to draw the linkage. So the value of theta should be provided. Okay, so for at this particular instant, this is the configuration of the mechanism. Say theta is 45 degree. Now, when theta becomes 30 degree, it will come over here, it will go there, and it will be like this. So velocities will obviously change. And the input link is 2, and the input motion given is omega 2, or n2 will be given. If it is n2 is given, you have to convert it into omega 2. Okay, so this is the forward linkage. Input motion given is, say, n2 given to link 2, n2 is given. If it is n2 is given, we can determine the value of omega 2. So what we like to determine through this velocity analysis, we have to determine the velocity at B here. Omega 4, the angular velocity at 4 of the link 4, and omega 3, angular velocity of link 3. Okay. So this is the given task. So forward linkage is given with all the link lengths and everything given, value of theta given, n2 or omega 2 value given. So we have to determine the value of velocity at B, the angular velocity at 4 and 3. So that is the task. So what you have to do? First, you have to select the space scale. Say 1 millimeter represents 5 centimeter of the link and so on. And the velocity scale. Okay. Now, just to help or facilitate the analysis portion, at the beginning, I'm showing you how the velocities are getting transferred. Because normally we do not need to draw all these things. Only directly the velocity diagram can be drawn if we are using relative velocity method, or directly if you are doing the, if we are doing the what is called instantaneous axis method, then we can directly draw on the above the mechanism. But for the beginners, we have to learn, we have to know how this analysis is actually taking place. Actually, if this is the link, if this is a mechanism, then we can disconnect all the links and see what happens. Velocity at point B, which is on link 4 and link 3. Similarly, omega 2 is given. We want to determine what is omega 4. So normally we can apply this concept of relative velocities or all other things if they're on the same body. So that's how we have to look for the common points or the joints. So if we analyze separately, it will look like this. So first, input motion is given to link 2. So we draw the link 2 separately. So this is link 2. Okay. So this is his orientation. This value is theta. Fine. Omega 2 is given. So what is the velocity at A? Because A is a known point where the other link is connected with it. So velocity at A will obviously be perpendicular to O2A, because O2 is fixed and A is rotating about it. So velocity is always perpendicular to that. So at any point on this link O2A, the velocity is always perpendicular to this because it is having a pure rotation. Okay. Now, 2 into its distance from the center of rotation, that is QO2A. So this is this. So we know its direction. Direction is perpendicular to O2A, and its magnitude is omega 2 O2A. Okay, fine. Then that velocity we're going to utilize for determining the velocity at 4 at B. Now where is B? B is at here. So from 2, we can go to link 3. So 2 and 3 are connected through a joint A. It's a revolute pair. There is only relative rotation is allowed between 2 and 3. And so point A is acting as a hinge point. So there is no relative velocity between 2 and 3 at A because they are connected. Their velocity is the same. And using that thing, we can analyze the velocity on link 3. So this is the link 3. So point A velocity is known, VA, because there is no relative velocity at this point, provided that this sort of joint is there. Had there been a prismatic member, there would have been a relative velocity. But this is not so. This is a revolute pair. Okay. Now, so at A, considering link 3, it has got two ends, A and B. A is connected with 2 and B is connected with 4. Now at 3, A is velocity is now is totally known. So this is the direction, same magnitude. But at point B, we do not know what is the magnitude. Okay. And neither we know the direction. If we consider only 3, neither we know the direction. But if we next take up the third moving link, that is link number 4, again it's a crank, it is fixed. It is having a rotation with respect to O4. So it is having a rotation and its sense will obviously be same, because if the input link moves in a clockwise direction, output link also should move in the clockwise direction. But if we do not assume anything at the moment, we can be certain that since this link is having a rotation with respect to O4, its direction of velocity at any point on this link should always be perpendicular to this link, because it's a pure rotation. So at point B, the direction of velocity is perpendicular to O4B, either towards right or left. We are not going for any conclusion at the moment. Let us find out what will be the direction. So it will be either towards right or towards left, but it has to be perpendicular to O4B. Okay. Now, so seeing all the 3 moving members separately, we get some idea about the direction of velocity B from over here. So that this B and this B are the same point. So here the direction of velocity will be either this direction or that direction. And since if it is moving in this direction, sense is this, it is supposed to be in this same sense, and in that case it will be in this direction. Okay. So these are the velocities with respect to the links when disconnected totally. Now let us determine what is the velocity polygon, and in order to do that, we use this expression, that the velocity at point B. So now V and A are there, present only on link 3, because only on link 4 it is B. Only link 2 it is only A. Only at 3 both A and B are present. At A, velocity, direction and magnitude is known, and B, the direction is known but the magnitude is not known. Then we apply the relative velocity method. So we choose a pole. So this is the pole. So the totally known vector is VA. So we draw VA in the same direction, same magnitude, to scale. So this is this. For B, we draw it accordingly. This direction, so we are according to direction, we put a line. Okay? And it is obvious because it is rotating clockwise. So this member will also move it clockwise. Okay? So if this one moves clockwise, it cannot move anti-clockwise. It has to move in that direction only, because this one is forcing it to move. Through this link. Okay, this one. But we have to complete the of B with respect to A. So that's the relative velocity. So how do we get the relative velocity? So far we didn't discuss about the relative velocity. So relative velocity in between 2 points on a link on the same member What is the direction? Magnitude you do not know, but what is the direction? Direction is perpendicular to the link. Perpendicular to the link. Why it's perpendicular to the link? For example, we take any link, say this one. Its center of rotation is this. If it is moving like that, so velocity at A is perpendicular its magnitude with this. What is the velocity at some other point? Say C is a point over here. So its velocity direction will also be perpendicular to it, and its magnitude will be O to C into omega. But its direction is always perpendicular to it because it is rotating. Similarly, member AB is also rotating, but its center of rotation is not known to us. That's why omega is not known to us. But if we consider the relative velocity between A and B, there will be no relative velocity along the member. The velocity will be perpendicular to the member. So if we want to know the velocity at B with respect to A, it will always be perpendicular to that. So we utilize that information here. So at point A, velocity is totally known. So we know this length, we know this point. And we also know the orientation of AB. So we drop a perpendicular to AB and that line and draw a parallel line to this. So this line is actually perpendicular to this. So we drop this line. So this line intersects the line of action of B at this point. So this is the point where we get the velocity triangle closed. So this point we identify. So join this and this. So this will give you the velocity at B, and this will give you the relative velocity of B with respect to A or VBA. Okay, is it clear?
Yes, sir.
Okay. So once this velocity polygon is complete, then our next task is to calculate the value of VB. So what will be VB? This length O4 O that's the polygon to this point multiplied by the scale factor that already we had selected. Okay. What is the value of the relative velocity? That will be this length multiplied by the velocity factor. Okay. Now, whatever VB we calculate, so that VB divided by this length will give you the value of omega 4, because VB is this. What is omega 4? Omega 4 into O4B is VB. So omega 4 is VB divided by O4B. So this is omega 4. And what is omega 3? Omega 3 is actually this relative velocity, whatever you have calculated, divided by AB, this length, will give you the value of omega 3. Okay. So this is how the analysis can be made complete. So our task was to determine these factors, VB, omega 4, omega 3. So this is how we do it using this relative velocity method. And for your convenience, this is shown separately, but actually do not need to draw them separately. Only drawing of this mechanism to scale, and then later on this velocity polygon is enough. And why we need to draw this to scale? Because when you will be drawing these directions of velocities, so velocity here has to be perpendicular to it. So if you do not draw it to scale, so direction will be wrong. Similarly, for the relative velocity, it has to be perpendicular to this. Relative velocity between A and B, it will be perpendicular to the direction correct for the relative velocity when we draw the velocity polygon or velocity triangle in this case. Now, same problem. Suppose we use instantaneous axis method. You will see it will become easier. What do you have to do? Obviously, you have to first choose the velocity scale, space scale, velocity scale, and so on. But the entire thing is done on the mechanism itself. So this is the mechanism drawn to scale. Okay. Then this is the input link. What we do? First we determine this velocity. over here, both magnitude and direction. Okay, that is the only thing that you can get as you have done earlier. Omega 2 multiplied by this distance, and this is the velocity. We have to find out in instantaneous axis method, we have to find out the center of rotation of all the links. In case of a 4-wall linkage, 4 members, one is fixed. For member 2, it is a fixed center of rotation. For member 4, it is also a fixed center of rotation. So velocity is always perpendicular to this member. Here it is rotating clockwise, so velocity is in this direction. Here for member 4 also, because it's having a fixed center of rotation, its velocity is perpendicular to it. And here, because the driving link is moving in clockwise direction, it will also move in a clockwise direction, so it will be there. So it will have a perpendicular to this. Okay, but we do not know its magnitude at the moment. So what is the center of rotation left? It is left for the member 3. So what is the center of rotation for member 3? You have to determine. Okay, so how to do that? It's very simple. For any link, if it is center of rotation is known, we know that the velocities will be perpendicular to the link, and it will be in the same sense out of the sense of rotation. If it is clockwise, here it is towards the right. If it is anti-clockwise, it will be towards left and perpendicular to the link. In case of a link whose center of rotation is not known, we apply the same thing in the reverse manner. Say for the link 3, that is AB, its center of point A and point B. Point A velocity is known totally, its magnitude and direction. So if the center of rotation is known, we know the point to be joined with the center of rotation and the velocity perpendicular to that. In case of when velocity is known and center of rotation is known, where will be the center of rotation? It will be perpendicular from here. So this is a velocity perpendicular. Velocity will be perpendicular in this direction. We do not know its magnitude. Okay, so if somewhere, so we drop a perpendicular to that. So these two lines, because A and B are on the same member, same link 3, intersect at this point. So this is the center of rotation for link 3 at this instant, because this O3 is changing its position. It is not having a fixed center of rotation, it is changing. That's why it's called instantaneous center. So at this instant, O3 is the center of rotation of link 3. Okay, so we have determined this instantaneous axis of link 3. But why? What should we do with it? Again, go back to the problem. Our objective is to determine the velocity and angular velocity of link 3, angular velocity of link 4, and velocity at V4. Fine. So once we get O3, are we in a position to determine the angular velocity of link 3? Yes or no? And if yes, how? How it is to be determined? If you have understood the thing, you should be in a position to answer that. What should be the angular velocity of link 3? How to be calculated?
center rotation calculation হবে কি?
O3 থেকে ডিসটেন্সটা বের
Right.
করব।
See, for link 3, this is the link actually, yeah? And it is center of rotation is this. So how to get and the velocity at point A is known, isn't it? See, for link 2, what we did? Angular velocity was given, center of rotation was known. So how did we find the velocity at A? It was omega multiplied by the distance. Here, the velocity is known, distance is known. So what will be the value of omega?
V by R use করব, V by O3 এর distance use করব।
So this velocity divided by this distance, isn't it? The same thing. Here velocity, considering link 3, velocity at A is known and its center of rotation, distance of point A from its center of rotation is known, that is O3A. So it will be VA, this is this divided by O3A. VA divided by O3A. So that will be the angular velocity of this link. Right? Clear?
Yes, sir.
So next target is to find out the velocity at B. What is the velocity at B?
তো O3B into same omega টা
It will be by the same way omega 3 multiplied by O3 into B. Because it's the same link, distance of the point B from its center of rotation is O3B. This is this multiplied by its angular velocity, that is omega 3. Okay. So in that way, we get the velocity at B. Next is, what is omega 4? What is the value of omega 4 then?
Sir, VB by BO4.
VB by
BO4.
Now, when you are considering omega 4, it is actually for the link 4. Okay, so it will be BO4. So it is VB divided by BO4. Okay. Now, if we want to know, get the velocity at some other point D, what should be its value? VD.
Sir, omega by D by O4.
What should be the value of omega by? No, why should be omega by?
Sorry,
omega 4
sorry.
into
Yes, sir. Omega 4 into
omega 4 into DO4.
D into O4.
This length into its omega. Okay. Now all these values we have calculated, particularly for VB and these we have calculated analytically, but the same thing can be done graphically also. Because you see here, if we know this velocity can be calculated like this. So this is perpendicular to this. So to take this arc and bring it back to this point, and you join this tip in that tip, and this is the point. If you drop a perpendicular from over here, whatever value you get, this is the velocity at point B. Like this. Say consider this link O2A. Okay, velocity at A is this much. Right. Now, suppose we want to determine the velocity at some other point over here. There are two options. We determine the distance from O2 to that point and multiply it by omega 2. But for that, you have to make calculations. But without making any calculation, still we can calculate. What do? We simply join this tip and the center and form a triangle. Then any point on this line will have velocity perpendicular to it. So drop a perpendicular. The point where this perpendicular intersects this line of the triangle will give you this velocity vector. So this is the velocity at point D. At some point, this point, if you drop a perpendicular, so whatever length you are getting, this is the velocity at this point and so on. So without calculating, just by making this graphically, you can calculate the velocities. Similarly, here, if BB is the velocity, once we get it, we just simply join from the center. So we get a triangle. So at point D, the velocity will be perpendicular to this line. So drop a perpendicular. And whatever length we are getting, so that is the velocity at point D. Of course, we have to multiply it with the scale factor. Why it is so? Because velocities are omega into the distance. Okay. So it is proportional to the distance. So here it will be O4B, it will be O4D. So it is proportional. And graphically, whatever is by drawing a triangle, we are actually doing that. So by dropping a perpendicular, will give you the velocity at d. Okay, so this is how, by using instantaneous access method, we can determine the velocities in a very fast way, very quickly. We can do that. Similarly, here also, once this center is identified, we can we know this velocity, join this point, and from over here, you take the same arc and same arc and intersect here, and drop a perpendicular. So this will actually give you the velocity at b. Simply cut this amount here and you get the velocity at b. Okay, you have to practice it actually, otherwise it will be very difficult for you to do. Okay, now I'm giving you certain data, particularly these two problems I'm giving you to for solving. You just copy these two problems. This is problem 1, this is problem 2.
স্যার
Hello?
স্যার আগের দিন ওই ডিগ্রি অফ ফ্রিডমের 5টা সাম দিয়েছিলেন, তার মধ্যে স্যার আনসার গুলো তো আমরা পাইনি স্যার। স্যার করেছি স্যার, লাস্ট একটা পাইনি।
তোমরা যারা যারা করেছো আমাকে মেল করে জানিয়ে দেবেন, দেখে নেবো পরে। ঠিক আছে?
স্যার
তোমাদের সলিউশন গুলো আমার কাছে পাঠিয়ে দেবে মেল করে।
আপনার মেলটা পাবো কোথায়?
যে মেল থেকে ইনভিটেশন যাচ্ছে ওই মেলে পাঠাবে।
Done, sir.
Okay, so I'll stop here today. We'll have our next class on Tuesday at 11. Okay.
Okay, sir. Thank you, sir.
Thank you, sir.
Okay. So
Thank you, sir.
work out these problems.
Thank you, sir.
Because these are graphical things, it will be difficult. There are a lot of difficulties initially when you do it. So practice it, okay, and give me feedback how it is working.